Okay, so it's my pleasure to welcome Daniel, who will be talking about recent advances in reverse computation of Poincaré maps. Yeah, thank you again for the invitation.
Yes, thank you, Boumedine, for invitation. And I would like to say that the topic is already suggested by Boumedine, and the talk will be very technical because I'm going to speak about algorithm. But at the end, I would like to mention also some applications because this algorithm has been motivated by applications we kept in mind. So this is a short list of applications we already did using these kinds of algorithms. We have a software you can download for free from that webpage, CAPD, etc. The cryptonym stands for computer-assisted proofs in dynamics, and we have already success in validation of some periodic orbits, coordinating orbits between periodic orbits for both ODEs and PDEs, computation on invariant tori around elliptic periodic orbits, and some local and global bifurcations like Cherenkov orbits or homoclinic tangentials for ODEs. Also chaotic dynamics in the sense of symbolic dynamics, and a couple of years ago I also shown the existence of hyperbolic chaotic attractor in some four-dimensional system. So as I said, the talk will be very technical, and first I will introduce the main object of interest. So what is the Poincaré section and Poincaré map? By Poincaré section, we understand some connected manifold of dimension 1, which is not tangent to the flow at any point. Here's a typical picture, and usually the Poincaré section is some hyperplane, but in principle it can be nonlinear. And from practical point of view, it is very convenient to look at Poincaré section as a zero level set of some function, of some smooth mark function. So by this notation P alpha C, I will understand Poincaré section given as a pre-image of zero of smooth function. Moreover, I assume this transversality condition, and also sometimes it is very convenient to add some additional constraints on the section, like crossing direction. For instance, we want to check the sign of function alpha from minus to plus or vice versa. We can also restrict the domain of intersection if necessary. So this is a predicate that stands from some restrictions, additional restrictions. And given Poincaré section for a flow, we can define a function which is with domain Rn to R. This is the return time. So as you can see, our return time is not a function from section to section. This is a globally defined function, of course, provided the argument belongs to the domain. So x belongs to the domain if there is a positive time, so that the trajectory of x crosses the section. In such a case, we define the function t pi of x as infimum over all these times t such that x of t belongs to pi. And here is an example. Given two sections, P1 and P2, sum of points starting from P1 can reach section like this one, or some of them not. And the last very classical definition, if we have two Poincaré sections, we define Poincaré map between two sections, P1 and P2, by the following formula. Here we evaluate x at the time, which is the return time of x from section P1 to P2. And we denote this map by P, by the letter P. And the primary goal of our algorithm is to compute the following quantity. Given fixed point y on section, on destination, on section P2, and given some coordinate system A, and given some set of initial conditions, we always play with set. The entire algorithm is about computation of Poincaré map over some domain. So this is our domain X, and we want to enclose this quantity. So this is not exactly the Poincaré map on the set of initial conditions X, but we want to enclose this intersection with section P2 in some coordinate system A. And let me explain why this is important. Here is some motivation and the simplest case of some affine Poincaré section. Assume that P is our hyperplane and this is our Poincaré section, and we have some y which belongs to P2. And we fix some coordinate system B such that the first column of this matrix B is direction of projection onto section. So this is our vector B1. And the remaining vectors form a base of our tangent space to P. In this case, this is exactly the space P. And if we compute this quantity, P of X, well, if we enclose Y as, if we compute Y which encloses this quantity, A times P of X minus Y for all X belonging to some set X, then what we get is a representation of our intersection of set of trajectories starting from X in affine form. This is very profitable and we can reduce many overestimations keeping this representation. I will give you some examples later. So this is the main motivation. Do not compute the intersection of set of trajectories as a product of intervals, Cartesian product of intervals, but rather try to align it to some coordinate system. And as I said at the beginning, my talk will be quite technical, so I need to introduce some basics of how rigorous ODE solvers work, at least some of them. This is the main difference between rigorous solvers and approximate solvers. For approximate solvers, we just take an initial condition and using whatever method, Runge, Kutta, or Taylor, whatever, we compute an approximate trajectory. In contrast, rigorous solvers take a set of initial conditions. The set can be represented somehow in the computer memory. And we want to first prove that the trajectories exist over some time range. And secondly, we want to enclose it somehow, this result. Of course, this enclosure should be as tiny as possible. So on that picture, we assume that red is the true image of the flow, starting from the blue box, and we enclose it somehow. In this case, into the, say, rectangle. Yeah, so this is our input to the algorithm which computes rigorously the trajectories. We start from a set of initial conditions, and the set of initial conditions can be represented somehow in computer memory. For instance, this can be an interval vector, so that this is a set such that on each coordinate we have an interval of possible values. We can represent initial set of initial conditions as a zonotop or Taylor model. Taylor model is a range of some polynomial plus some remainder. On input, we also have some trial time step from prediction we want to make. And at the end, we want to compute first that the trajectories exist. And secondly, we want to compute as tiny as possible enclosure of the set of trajectories after time step. So we want to compute Y. This is the rough enclosure. Rough enclosure encloses all possible trajectory segments starting from points X from the capital set X over the time step. And X1 is an enclosure of the set of trajectories after time step H. So how to compute Y first? This is our strategy. We have some X. This is our set of initial conditions. We want to compute blue, actually, the set after time step H. By the way, we need to validate that the trajectories exist over this time range. So we want to compute the rough enclosure, which is marked here by green color. This is the very basic strategy, just to give you some feeling how it works. But of course, there are more advanced methods to compute enclosures. Here is a little theorem, well known. Assume that we have some guess. Y is a convex set. This is given from some prediction. And if we can enclose interval hull of this quantity, so we add set of initial conditions to all possible directions of vector field for the times between 0 and h, and this inclusion holds true, then Y is a rough enclosure for the flow. This is an example how it works in practice. Given this vector field and this particular time step, and red is our initial condition, set of initial conditions. This is that box. We guess blue as possible enclosure, and this guess is obtained by computing f of x here instead of f of y, because we don't know why, but we enlarge a little bit the range 0, 1 to something negative is something larger than h. This is our guess, and computations in interval arithmetic gives the following bound. After that, we compute the quantity x plus time range times vector field over predicted enclosure. And because inclusion holds true, we proved that the blue set is really an enclosure for the trajectory starting from the red set. So this is just a very basic idea that we can really validate that the trajectories do exist over some given explicit time interval. And in order to compute tighter enclosure after the time step, usually we use higher order methods. We can also use higher order enclosures as proposed in paper by Nedialkov and Jackson. What we just compute is the higher order polynomial approximation to the flow, and on that we build a candidate for enclosure, and then we validate it by checking just this inclusion. This strategy is very, I would say, it works in practice very well. Moreover, rigorous methods are very sensitive to so-called wrapping effect. If we enclose the set of trajectories all the time as a product of intervals, what we get is extra overestimation. In order to reduce this extra overestimation called wrapping effect, we often propagate coordinate systems along with the set. So instead of representing the subset of our phase space as an interval vectors, we represent them in more complicated ways, like a fine representation. So this is our center and some matrix, which stands for the shape of our set. This is the doubleton representation. So this is just a fine representation plus some extra errors. Here we have an example of tripleton representation where these errors are represented as in two different forms and then intersected. We can also use ellipsoid sets, Taylor models, etc. But what I would like to emphasize that we have some representation in order to reduce wrapping effect. And now I guess I'm in point to describe the main idea of our algorithm, because it heavily relies on internal representation of sets in our underlying solver. Our constraints. We want to compute intersection of a set of trajectories with our Poincaré section. And we want to do that without subdivision. Why? Because the decision on subdivision should be made on higher level. For example, we have infinite dimensional system, and then subdivision in infinite dimension is rather difficult. So we want to make this decision about subdivision on higher level. This algorithm should avoid subdivisions. Moreover, we would like to take advantage from the extra knowledge on, for example, local behavior from non-rigorous approximation of the Poincaré map. We want to reduce wrapping effect, extra wrapping effect on the section. So what we are interested in is this green segment here, and not that set. Okay. This is extra wrapping on the section. We want to just obtain this segment. Moreover, we would like to take into account internal representation of the solutions in underlying ODE solver. If the ODE solver represents sets before and after section in that way, in gray way, we don't want to enclose them. Because if we enclose them, we introduce extra errors. when intersecting the section. Okay. Okay, so I assume that we have two abstract algorithms. By abstract algorithm, I understand data type-dependent algorithm. If you are familiar with object-oriented programming, this can be achieved by either virtual functions or templates in C++, for instance. So I assume that we have some data structure, I call it a representable set, which describes somehow a representation of our set of trajectories. For example, this representable set can be doubleton, like here. And I assume that I have type-dependent algorithm, I call it affine transformation, affine transform. This algorithm should compute this quantity, matrix times x minus y, in as efficient as possible form. So given representable set and some linear map and some vector, I want to enclose this quantity. For example, if my representable set is doubleton, I can enclose this in the following way. First, I can evaluate my expression and multiply this box by matrix A subtract y, or I can first multiply matrices, which means I change coordinate systems first, and then I multiply new coordinate system by boxes R0 and R. Of course, both representations are correct, so I can intersect them. So this is sample implementation of affine transform in the case when my representable set is doubleton. The second algorithm, also type dependent, is called eval. By eval, I assume abstract evaluation of some abstract function g on the set of x's which belong to some representable set. So I want to enclose g of x when x is some representable set. Of course, this is type dependent. Here is some implementation in the case when our set is represented as doubleton. So again, assume that our set x is given in that form, an evaluated expression, and we have a smooth function g. Then we can enclose this g of x in two ways. First possibility is to just use interval arithmetic. So I can enclose the range of g over the set x, where x is evaluated expression here. Or I can enclose derivative of this map over set x. This is an interval hull, so this is a convex hull in particular of our set of matrices. And then I can apply mean value theorem. So first I propagate products of matrices here and there, and then I add these quantities, and this is another enclosure of our g of x. Of course, I can intersect them. So this is sample implementation of this abstract algorithm for the case when representable set is just a doubleton. This is an algorithm which computes return time. Computation of return time, rigorous computation of return time is actually very easy. We can integrate our set of initial conditions until we are very close to section at time, say, t1. Then we can do some little time step to make sure that we are after section, so at time t2. And enclosure of set of trajectories between t1 and t2 is our enclosure for the Poincaré map, and also we obtain a bound for the return time t1 to t2. But usually this return time is very large, and we want to shrink it as much as possible. So this is the first algorithm of which is a step in our computation of Poincaré map, shrinking return time. So at the beginning, we assume that we have already a return time t1 to t2, and we want to compute tighter bound for this return time. This is our algorithm. First, we take a midpoint of our interval. Then we compute representable set, which encloses a set of trajectories starting from the set just before section and moves this set to the mid time of our interval. So x0 is expected to be a set just on the section, very close. Then we eval function alpha, which defines our section on this set x0. And here we use representation of our set x0. Then we compute enclosure of entire trajectory segments for all intermediate times. So here we have time range. And what is at the end is just intersection of the bound we had already with some interval Newton operator which acts for one-dimensional function. And this is the geometry of our algorithm. X1 is just before section, X2 is after section. We shift a little bit set X1 and we expect it is already very close to section. Then we compute a value of alpha using this representation of our X set, and we apply interval Newton operators. This slide explains why this function eval is so important. For example, if our set is represented in this way, X plus C times R, this is our center of our set, this is shape matrix, and this is a box. Okay, we can evaluate this in interval arithmetics directly. So our section is given by X minus Y. So this leads to the following bound. So we can decide whether the set is out of section or not. But using the mean value form and eval algorithm, we first evaluate the section at the center point of our set. So what we get is epsilon, epsilon, epsilon. Then we multiply a gradient of our section times shape matrix, and then we multiply it by the box. What we get is 0 here. So this evaluation using taking into account representation of our set in evaluation of in enclosing values of functions is very important. At the end, we get point value, and this is a large interval here. Second algorithm computes Poincaré map. We have bound for return time. This bound is returned by the previous algorithm, and we have x1, which is just before section. F is our vector field, y is a point on the section, and A is some matrix. We want to enclose this quantity. And the algorithm consists of the following steps. First, we compute very rough enclosures, just enclosed set of trajectories for all intermediate times starting from x1. This is the very rough bound for the result. Then we want to improve it. As before, we compute the midpoint of the return time interval. Delta t is displacement from t0. As before, we move a little bit our set x1 to the center. We call it x0. And this is the very important step. Here, we compute a fine transformation of our set x0, taking into account representation of the set. This is the absolutely crucial step in our algorithm. Then we compute two quantities, y, which is evaluation of matrix A composed with our vector field at our set x0, and we multiply it by delta t, this time displacement. And delta y is just error term coming from Taylor expansion. I will show you later. It turns out that this sum y0 plus y plus delta y is also an enclosure of our Poincaré map. Well, not Poincaré map, of this quantity. So what we get is this quantity represented as a sum of three boxes, y0, y, and delta y. And as I mentioned, y0 is the primary part of our result, the main component of our result. We want to make y and delta y as small as possible. And this can be achieved either by playing with coordinate systems, or playing with sections, or playing with projections we used to define this matrix A here. A little slide about correctness of this algorithm. So T is our crossing time interval from 0 all trajectories intersect our section in time t, which belongs to this interval. So our Poincaré map for every x belonging to x is a subset of this set, phi of tx1. Then we shift a little bit x1 two times t0, which means this is equal to that quantity. And here we use Taylor expansion with respect to time. So this is just x0 plus a vector field at x0 times delta t and second order terms. And multiplying this by a and subtracting y, we get a times x0 minus y. And this is our affine transform. This is our quantity a times f of x0 times delta t, and this is our y. And this is delta y. As I said, y0 is computed as a affine transformation of our set of set on the trajectory denoted by x0. Good. And here is a geometry of our algorithm again. We have x1 before section, move it a little bit, use affine transformation to compute the main component of the result, which is y0, and then add some error terms, y and delta y. Okay, here is a little example. We want to make the terms y and delta y as small as possible. To give you some motivation, let's consider a very easy example of van der Pol oscillator. And we can consider two sections, either classical section defined by y equal to 0, or use some extra strategy to choose sections such that the return time is very flat function. We have two scenarios actually. First scenario corresponds to the case when we cannot change the section. This happens, for instance, in hybrid systems when the sections are guards between different vector fields. We cannot modify this section. Sometimes we are free to choose the section, and if it is possible, it is often worth to do that. Here is an example. Changing a section from that segment to that segment, we can minimize crossing time. First strategy, we want to make delta y and y as small as possible by a proper choice of our matrix A. So we have a little theorem. If we assume that our matrix A is chosen as an inverse of the following coordinate system, f of y is the first column of our matrix B. So this is a vector field at the point y. And the remaining columns span tangent space of our to our Poincaré section at point y. Then the error terms are of that form: delta t at the first component, then zeros, plus something which is small in comparison to the diameter of our set x0. And the main motivation is the following corollary from this theorem. If our section is hyperplane, then what we get is our bound for Poincaré map P of x as an affine in affine form. So our bound is computed as y, which is given at the input to our algorithm. B is also input to our algorithm, but then we can skip the first coordinate delta t, which can be large. And what is left is the matrix shape times something which is computed by as a sum of our three components, but those two components are small in comparison to y0. Okay, so the main component of our result is y0, and because we skip the first coordinate, which can be large here, what we add are quadratically small components to the primary to the main component of our result. Here is explanation of this algorithm. Our set y is computed using a mean value form. So we want to enclose f a times f evaluated at our set x0 times delta t. But we use mean value form. So this is assumed to be 1, 0, 0, 0 because we have chosen the matrix A in this way, such that A times f of x0 is just the unit, well, this vector. And A times derivative evaluated at entire set x0 can be quadratically small in size of x0, because here we have delta t, which is also proportional to the diameter of the set, and this difference is also proportional to the size of the set. So in total, what we get is quadratically small component, this component. So at the end, what we get is this quantity times quadratically small quantity, but in this quantity we skip the first coordinate. So this is why it is small. And let me show you some results of experiments. We will show it on 4 examples, 4 periodic orbits. This is periodic orbit for Michelson system for Faulkner's scan equation. Those are 3-dimensional ODEs. And the first is very classical. Second is chosen because of some very specific reason I will explain later. And this is periodic orbit for 4-dimensional Rosler system, which is hyperchaotic. And this periodic orbit has 2 positive Lyapunov exponents. And this is the same system, 4-dimensional Rosler system, but in the case when one parameter is chosen so that this orbit is exactly at period doubling. So one of the eigenvalues is equal to -1. And this is a data. Michelson system is that system. This is our initial condition for periodic orbits, and derivative eigenvalues of Poincaré maps are like that. So this orbit is hyperbolic. For Faulkner's scan equation, we have approximate periodic orbit and also hyperbolic eigenvalues. This is the Rosler system, and this orbit is also hyperbolic. -2.9, something just above 1, and the third eigenvalue is very, very close to 0. So this is actually some numerical noise. And the fourth orbit, as I mentioned before, is close to period doubling. So the one of the eigenvalues is very, very close to -1. And what the main settings of our experiment are the following. We choose a set of initial conditions centered at approximate periodic orbit. We build a box on approximate eigenvectors, and we want to enclose Poincaré map for every point starting from this black set. What we expect, if the set is small, what we expect is that the shape, well, the image of the black set should be more or less linear, close to linear approximation of our Poincaré map. So it should be scaled by eigenvalues, like this blue one. So here we have some expansion, here we have some contraction. And we have 3 strategies. First is a very naive strategy when we choose just A equal to identity as our coordinate system at section. The second case is when we choose eigenvectors on the section, but the projection vector is equal to, is chosen as a normal to the section. And a floaty strategy is when we choose B1 as a direction of our vector field. And this is, let me show you some data from computation. Just a second. I will just show you my our preprint because it is much easier to show these tables here. Okay, so this is for Michelson system, for instance. I hope you can see it. Let me explain what is in this table. In the first column, we have size of our set centered at our approximate periodic orbit. So this is set of size 10 to minus 13, 12, etc. What we get in the next columns is diameter of our set, which diameter of our enclosure of the set with Poincaré section using different strategies. So this is strategy with projection direction equal to normal vector to our section, and this is the flow view strategy. This is our eigenvalue. So we expect that scaling will be very close to our eigenvalue. Flow view strategy, as you can see, very exactly keeps the shape. This is our first larger eigenvalue. And for initial sizes of sets up to, say, 10 to minus 3, this is just scaling by the eigenvalue. And the same happens for the second eigenvalue, which corresponds to contraction. You can see that normal strategy is very bad here in comparison to flow view strategy. So flow view strategy keeps the shape up to 10 to minus 44, sorry, more or less. The same happens for Faulkner's Kahn equation. This is just scaling by eigenvalue here and there. And also for Rosler system, maybe the period doubling orbit I will show you. Okay, so here we have eigenvalue equal to -1, and we can see that our algorithm keeps the shape up to, say, size of initial condition 10 to minus 3, more or less. Okay, so this is the first strategy, playing with coordinate system. If we choose properly projection of direction of projection, and we choose the coordinate system on the section, we can reduce wrapping effect on the section. Second strategy comes from the fact that we can play with section itself. So we want to make those two quantities y and delta y as small as possible, but also playing with the section. And here is a little observation. If the section is chosen so that the return time is almost constant for our set on initial condition, then this crossing time is smaller, tighter, and probably also the bound for Poincar map will be better. And this is our main theorem in this, say, paragraph. Assume that we have a periodic orbit of period t. And we always have that lambda equal to 1 is eigenvalue of monodromy matrix. This corresponds to the fact that our time direction is neutral. And assume that left eigenvector, well, sorry, and assume that our eigenvector lambda equal to, eigenvalue lambda equal to 1 is of multiplicity 1. Then our return time is flat. It has local extremum, for instance, at our periodic point, if and only if this section is chosen so that it is orthogonal to left eigenvector of our matrix M. So in this case, our return time is a flat function near periodic orbit. Here is some explanation of this. So, well, one implication. So here are some notion. Alpha is our section, M is our monodromy matrix. This is an identity which defines our section. So our alpha section, alpha function which defines our section is constant on these arguments. We differentiate it with respect to x, and because alpha of x is left, this one form is left eigenvector for this matrix M, we can replace quantity by that one, and this means that these two forms are proportional. So they have the same kernels, but one kernel of alpha is just our section. So this is more or less explanation why it works. Here is an example on van der Pol equation. Choosing naively our section y equal to 0, we compute rigorously bound for Poincaré maps for a set of initial conditions centered at approximate periodic orbit of that size. The first column in this table shows the diameter of crossing time, bound for the diameter of crossing time, and the second column shows the bound for Poincaré map, so in this red line segment. We can see that the diameter of crossing time increases more or less linearly with the diameter of initial set. In the second case, we choose the section according to the previous theorem. And we see that crossing time, diameter of crossing time is quadratic, more or less, with respect to size of initial set. Here we have some constant value because we are on machine precision, so cannot be smaller. Of course, we can make these numbers smaller using higher precision interval arithmetics. Okay, this is a warning actually. I call these sections, which are chosen according to the previous theorem, CTO, crossing time optimal sections. But it may happen that these sections are very tangent to the flow. This is exactly the case for Faulkner's scan equation. We can compute the angle, cosine of the angle between section chosen according to this theorem and the vector field. We get that along entire trajectory for Faulkner's scan equation, this is almost tangent. So the cosine is less than 0.04, more or less. This may introduce extra errors coming from sliding effect. Show tables again. The same tables actually, but we will analyze two extra columns. This is CTO section at the same point, and this is max angle CTO section. By max angle CTO section, I understand CTO section attached to a point on the trajectory in which the angle is the largest. And the results show that there is no so much improvement in comparison to flow deer strategy, the previous one. Why? Because flow deer is already very good, and this gives quadratically small errors, and there is actually no room for improvement for CTO and the max angle CTO strategies. The CTO strategy introduces errors of size of the diameter to the power 3 or 4. And quadratic errors are already very, very small. And moreover, I would like to emphasize that these numbers cannot be compared directly because what we are computing are different sets on different sections. So, for example, we integrate a different set of initial conditions because we are starting from different sections. Okay, and I would like to finish with some non-trivial, I guess, example, which shows that this algorithm is working in practice. Well, maybe first some piece of code on C++ code, because all these algorithms are implemented for many years and are part of the CAP library I mentioned at the beginning. In order to use our library, it's sufficient to, this is C++ library, first of all. We just need to include one header file, and this is the way we define the vector field. E stands here for interval version. We can replace it by D, which means double precision or long double precision or multi-precision, non-rigorous. I stands for rigorous computations. We define a map of 3 variables, x, y, z, and with components like that. If the expression is more complicated, we can define a map as a C routine. Based on this vector field, we define ODE solver. It takes a vector field as a parameter and order of Taylor method or Hermite-Breshkov method, say 20. And then we specify initial condition. Let it be a point. Can be box. Let me check if it compiles. Yes, it did. Then we represent somehow our set, say triplet representation. We can define Poincaré section. Like that. Our system is three-dimensional, and we can choose our variable as being our section as x equal to 0. So this is the first variable out of 3, like that. And in the end, we define Poincaré map. We have to specify solver and the section. And that's it. We can compute Poincaré map like that. Poincaré map evaluated at point, well, point represented in this way. So our representation of U is S. And I will print the result using just 5 digits. So maybe I change it to 17. Yeah. I don't remember if I correctly provided the order of the arguments here like that. Let me check again. Oh yes, this is the result. So we see that the section is given by x equal to 0. So this is our enclosure of the first component. It contains 0, and the remaining 2 intervals are bound for the y and z components of our result. Yeah. Another possibility is to use our algorithm I already mentioned. So we have to provide coordinate system in the center. So let me define, just to show you how we are using it, matrix, say A, let it be identity. I don't want to specify at the moment. Three-dimensional identity, and the vector, the center will be 0. Okay, so we can compute this in this way also. Not in this way. Just a second. Anyway, we have to provide here extra arguments for receiving this result in proper coordinate system. By the way, you can see the source code of our library. Poincaré map. And what is the syntax of this operator? It should be somewhere here. Set, the order is different. Okay, so I have to specify first the center, then the matrix, and then some return time. Like that. By the way, as a byproduct of this routine, we can compute rigorous bound for the return time. So let me print it also. And this is the result. So the return time, rigorous bound for the return time is this interval. And as before, we get the bound for Poincaré map. And at the end, I would like to show you some application to PDE of this algorithm. This is a Kuromatowski-Waczyński equation. And if we impose a 2 pi and odd periodic boundary conditions, we end up with this infinite dimensional ODE for Fourier coefficients. And here is a parameter μ for this system. And Wilczak proved in his paper in Foundations of Computational Mathematics 2004 that this system for this particular parameter has a fixed point, where Poincaré map has fixed points, so a periodic orbit. And I tried to reproduce this result using the new algorithm for Poincaré map. So here is the data from computation. This is our infinite dimensional box around approximate periodic orbits of fixed point for Poincaré map. Because this is an infinite dimensional object, so we represent the finite number of modes in explicit way, and then some geometric sequence which bounds the remaining coefficients. And the bound for Poincaré map in this case was like that. So we see that all these intervals are mapped into those intervals. So Brouwer-like version of infinite dimensional version of a Brouwer-like theorem shows that we have a fixed point for the map. But what I would like to emphasize that even if this infinite dimensional case, our solver and Poincaré map algorithm keep the shape. So this is an approximate eigenvalue, and we see that the initial size is scaled by this quantity, more or less. For higher modes, the system is heavily contracting, so this is just some noise actually. If we enlarge, decrease a little bit parameter μ, the system becomes chaotic, at least it is observed. And for this particular value of parameter, we observe this chaotic attractor. On this attractor, we can see fixed point and period to orbit. And this is the profile of those solutions. They are both time periodic and space periodic. And if we repeat the same computation for the blue fixed point for that one, we end up with the following bounds. This is our size of initial set centered at fixed point, and this is bound for Poincaré map. And here are also eigenvalues, approximate, of course. And this is, again, more or less some scaling by eigenvalues. And actually, obtaining proof of the existence of chaotic dynamic in this system would be not possible without this particular algorithm I explained before. This is the main result for this Kuramato-Szydlaczynski PDE. We were able to check some geometric conditions which are very close to this picture. That some wall of infinite dimensional box map to the left, to the right, and we have some shrinking. We were able to check that there is a chaotic set in the sense of symbolic dynamic for the system, and this invariant set H contains countable infinity of periodic orbits of arbitrary large principal periods. So the proof is a mixture of topological results and some numerics. And moreover, this is a paper in preparation. We are able to show the existence of countable infinity of connecting orbit between those two states in both directions. Yeah, that's it. Thank you for your attention. And are there any questions, perhaps?
Yeah, thank you very much. Any questions? Yeah, just have maybe a quick question at the very beginning when you say when you were talking about the computation. I mean, you said that you have a representative or of the sample. What does it mean exactly?
Okay, because we are playing with sets,
yes,
not with points, so we have to represent sets in computer memory. Okay, so we have to choose a class of sets which are representable. Of course, we can use a very rich set of sets, but then the manipulation of this rich structure is very complicated. So we have to balance between the speed and possible rich choice of possible shapes. So we restrict to say affine set, zonotopes, or doubletons. This family of set is rich enough to bound many subset of our phase space, but it is also very fast when it comes to manipulation of it. Playing with just intervals introduces huge wrapping effect. So overestimation, overestimation, and just after a few time steps, the results are useless completely. So keeping proper coordinate system and closing our result in some representation allows us to integrate longer and make some smaller errors. So this is in contrast to non-rigorous computation when we are interested in just single trajectory. This problem completely is not present in this case. The library I shown you also provides algorithms for non-rigorous computations of Poincaré map, just taking a point and compute Poincaré map or the derivative, etc., etc. So this is very easy, actually, in comparison to rigorous methods. Yeah.
All right, thank you.
I can switch my screen to Notepad and show you how it works for non-rigorous version like that. Say long double precision of the solver, vector, and say choose section, Poincaré map, non-rigorous long double precision, and then compute Poincaré map like that, non-rigorously. For the same system, okay? So in this case, we are interested in just single trajectory, not a set. Rigorous method proves that the Poincaré map first exists, and then we have a rigorous bound for that. This is just approximate result.
All right, thank you. Any other questions?
So as I said, my talk was very technical because
yeah, it was technical. Yeah, so yeah, I think it's yeah, I think I need to look at your paper more. So yeah. Yeah, okay. I mean, there are, yeah, thanks again for that. I just want to thank you on behalf of everyone else. And
thank you very much.
If you have no other questions, I mean, yeah, so thank you. Yeah, I mean, I'll contact you later. I probably have other questions. Yeah, thank you.
Okay.
Yeah, thanks a lot. Take care.
Have a nice day.
Bye. Bye.